What up, calculus students? Unit 1, lesson 1 homework. Due the day after your unit 0 test. Talking about limits. Key concept in calculus, limit. Limit says, don't look at the location, but look infinitely close to a location. If I ask you like what a function value at a location is, we're looking at the location, h of 0. Let's start with h of 0. When x is 0, when x is 0, here's 0 on the x-axis. What is going on in this location? I like to use like a vertical line, like right there. What's going on? Well, I have a y-coordinate here at 1. So h of 0 is 1. We have the point 0, 1 on the function. H of 1 is a little trickier because at the x-coordinate of 1, we got a couple open circles and a closed circle. Well, right here, at 1, the closed circle is saying that's the y-coordinate you use. So at the location 1, I have the y-coordinate of 1. Okay, so x's, y's. Now when we talk about a limit, this is when we look really, really close to a location, not exactly on a location. The negative sign in like the exponent of a number means to the left. So I'm going to look really, really close to 1 on the x-coordinate, but just to the left of 1. Okay, I'm talking about infinitely close to 1, just a little bit less than it. And you can use like a vertical line to help you. Like if I'm to the left of 1, this is like at 0.75 or something like that. You can see your y-coordinate is right here. Well, as this line, I can't move it over, but if I can move this line infinitely close to 1 from the left, I'm still using this piece of my function, which means as I get really, 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 really close to 1, but I'm just to the left of 1, my y values are getting really, really close to this open circle's location. This open circle's location is at 3. So that's why I say the left-hand limit of h of x as x approaches 1 from the left is 3. Now, if I have a plus in the exponent, that looks at something just to the right of a location. So the limit as x approaches 1 from the right, I go just to the right of 1. Okay. Now, if you use like a vertical line, you can see like just to the right of 1, I'm using this piece of the function, this one right down here. And if I move this line closer and closer and closer to 1, and I'm to the right of 1, my function is getting closer and closer to this hole's location, which is at a y-coordinate of 0 because it's on the x-axis. So that's why I say the right-hand limit of h of x as x approaches 1 from the right is 0. Now, the rule is if your left-hand limit equals your right-hand limit, the limit exists and it's that number, okay? If your right-hand limit and your left-hand limit do not equal each other, 3 is not equal to 0, the limit in general does not exist. This typically occurs at jumps. It also occurs at like asymptotes. So there you go. Does it matter that we had a point at 1? No. The limit does not concern itself with what's going on at 1. It's all about what's going on to the left and what's going on to the right. If we look at 0, well, to the left of 0, I'm right here. These points, as I get closer and closer to 0, just to the left of 0, I'm getting closer and closer to this point's location. This point's location is at 1. So that means the left-hand limit also is 1. To the right of 0, looking right above it or right below it, just like a vertical line, you can see I'm right here, but as I get closer and closer to 0, I'm getting closer and closer to this y-coordinate, this point, 0, 1, so this is also 1. The left-hand limit equals the right-hand limit. The limit exists, it equals 1. We'll talk about in lesson 2 how if your function value and your limits agree with each other, then this means the function's continuous at that location, okay? It's smoothly connected. There's no jumps, there's no holes. It's just like what we typically see with functions is that things are just smooth and continuous. The function is continuous at 0. The function is not continuous at 1. Let's do another one. Okay, this location is the location that everybody messes up on. So we'll make sure we spend plenty of time on that. All right, let's start with the function values. Let's start with what's going on at locations. So starting with the x location of -1. Here's -1. At this x location of -1, looking right above and right below, I got two situations. I got open circle here and a closed circle. The closed circle is what is being defined as the y coordinate when you plug in -1 into this function. So I would say that g of -1 is this y coordinate, -1. That's a x coordinate here. That's a y coordinate. At 2, at 1, 2, I look right above 2. I have an open circle and closed circle again. Well, that's telling me if I plug in 2, I'm going to get this y coordinate. That closed circle is like what is being defined if you plug in 2 in for your x coordinates for your function. And that's 3. So g of 2 is 3. Don't worry about the open circle yet. And then at 3, an x coordinate of 3, I can see my function's passing through this y coordinate of 0. So g of 3 is 0. Okay? But now let's focus on limits. Let's look at -1 to the left. Okay? That negative symbol means to the left. This negative symbol means I'm looking at -1, the x coordinate. All right. If I'm just to the left of -1, I'm going up here. It's not always going to be up. It's just the fact that if I drew a straight line through an x coordinate that's just to the left of -1, that here are my y coordinates. If I move this line closer and closer to -1, I would be tracking this function and I'd be approaching this open circle's location. So this is why -1 from the left is this y coordinate's location. It's 2. Now, if I were to do the same thing to the right of -1, I'd be thinking about plugging in x values just to the right. Okay? And I can see that my y coordinates are now down here in this piece of the function. As I move this line closer and closer to -1, but I'm just to the right of -1, my y coordinates are down here approaching this location of this closed circle. This closed circle's location is a y coordinate of -1. So x coordinate, y coordinate, x coordinate, y coordinate. Whoa. Since my left hand and my right hand limits do not agree with each other, since I got 2, since I got -1, I don't care about the fact that there's a closed circle, open circle. It's just I look at these numbers are not the same. This limit does not exist. Okay? Now let's look at 2. Okay. If I'm just to the left of 2, I'm right here. Okay? Now this open circle is very exaggerated. It's only an open circle at the x coordinate of 2. We're going to pretend like I could move this line over and that I would get really, really close to 2, and I would be getting really, really close to this open circle's location. If I plugged in something like 1.99999, infinitely close to 2, I would get a y value that's very, very close to this open circle's location at 1. So that's why I say the left-hand limit as x approaches 2 is going to be 1. The y coordinate that I'm approaching to the left of 1. If I were to do the same thing, but I'm to the right of 2. So here I am to the right of the x coordinate 2, and I can see my y coordinates are up here. As I get closer and closer to 2, to the right, I'm moving this line over. I can see my function's right here, and I would be approaching this location as well. That open circle's location's at 1. My y coordinate I would get if I plugged 2.0001 into my function would be something close to 1. So that's why I say as we approach 2 from the right, we're also going to approach that open circle's location of 1. Now, the limit in general, I don't care about this open circle. I don't care about this closed circle. I just care about what I see here with my left and my right hand limits. The left hand limit is 1. The right hand limit is 1. That means this limit is 1. But there's an open circle. Who cares? Doesn't matter. It's just to the left and to the right of 2. My y coordinates are getting close to 1. Done. 3 is the easy one because there's nothing crazy going on. We have a point and we are approaching that point. So my function value, my point is 3, 0. I'm approaching that point 3, 0 from the left, from the right, and I have that function value. We would talk about next class how the function is continuous at 3. Okay. Now let's look at this one. Let's start with function values for f. So f of -2, f of -1, f of 1. All right, f of -2, when x is -2, do I have a closed circle above or below -2? Well, I have an open circle, but that means there's no function value assigned when I plug in -2 into this f of x function. So since this is not a point, since it's not a closed circle, f of 2 is undefined. Okay, function values are either defined and equal a value, or they're undefined and they don't exist. We don't have a function value right above or right below -2. If you look at -1, we can see this y-coordinate of 0. So we got the point -1, 0, f of -1 is 0. If we look at 1, we're looking right at 1. I can see that I have a closed circle and an open circle. That closed circle is saying at 1, we have a defined function value. It's that y-coordinate 2. Okay? But this is not significant compared to when we start talking about limits. When I start talking about limits, I'm just going to ignore what I put down for my function values. I'm just going to look at to the left and to the right. So let's start with -2. If I'm to the left of -2, where are my function values? Down here. As I get closer and closer to -2, I'm still going to be getting function values. It's only at -2 do I not have a function value. But if I plugged in -2.001, which is a value that's like to the left of -2, I would get a y-coordinate that's very close to this y-coordinate, which is -2. So I say that y-coordinate, that limit as we approach -2 from the left, is -2. -2 from the right, I now take my line. I then think about if that line is to the right of -2 and to the right of -2, I'm also down here. And as I move this line closer and closer and closer to -2, my y-coordinates are going to be getting closer and closer to this hole's location, which is at -2. So -2 from the right is also the y-coordinate of -2. That's your x, x, x. I don't like how the values are the same, but it is what it is. Now, I don't care about what I did here. I don't care that this is undefined. I look at these two numbers. If the left-hand limit equals the right-hand limit, the limit exists, it equals that number. That's it. I don't care about the undefined thing. It's just left hand, right hand, boom. Either equals the value or does not exist. Now let's look at 1. If I'm to the left of the x-coordinate 1, here's my line. That's to the left of 1. I can see that if I plugged in like 0.8, here are my y-coordinates right here on this piece of the function. If I move this line closer and closer and closer to 1, my function's down here approaching the location of this open circle. This open circle's location is at -1. So to the left, I'm approaching that y-coordinate location, -1. If I am to go to the right of 1, I can see I'm up here now, right above or right below this x-coordinate to the right of 1. We're using these function values. If I move this line closer and closer and closer to 1, my function values are here, getting closer and closer to this closed circle's location, which is at 2. Does it matter that it's closed versus an open circle? No. It's just about like what we're getting close to. I don't care that I have a point, 1, 2. If I'm asking you what is the limit as x approaches 1 in general, I look at these two numbers. If they agree, boom, that's the answer, that's the number. If they don't agree, -1 and 2 are not the same, it does not exist. Okay? Now, we're going to use a calculator. I know I told you like calculators are not necessary. They aren't necessary. Like your Quiznex class, you don't need a calculator. I'll give you all the data that you need to be able to answer questions that are like this. Okay. I'll like fill out the stuff for you. The question is, what is f of 2? Well, like multiple ways to do this using your calculator. Let's get out a calculator. Okay. To find f of 2, we're plugging in 2 for x. I can, literally in my home screen, just plug in 2 for x. I know you guys love the fraction button, so I'm going to use it. If I plugged in 2, took it to the 4th power, subtract 16, I know I'm getting 0. And if I took in 2 and square it, I like to use parentheses just so my calculator doesn't make a mistake on me. That's interesting. There we go. I know I'm going to get 0 over 0. You're not allowed to divide by 0. My calculator is going to be like, nah, you can't divide by 0. Okay, so that's one way to see that like this is undefined. The other way, which I'd advise you to do, is to graph. Because we showed in class and on your video that your calculator does a very good job of finding function values very quickly using trace and plugging in a number. So I'm going to graph this, and I got that equation. I can press trace, and I can plug in whatever value I want. 3.123. I get that. 1.023. I get that. 2. Y is empty. Okay? So what that's telling me is that this function, though it looks like a nice parabola, actually has a hole. It has a hole at 2. Okay? There's a hole at -2 too. The question is, what is the limit? Okay, well, you got to think about it. If I were to ask you about limits, you should check the limit as x approaches 2 from the left of this function. And you should look at the limit as x approaches 2 from the right of this function. It's very easy to do this with a calculator because you can plug in whatever x value you want. Limits are talking about getting very, very close to something, not what's going on at that location. If I was to get very, very close to 2, but be just to the left of 2, I'd be at a x coordinate like 1.99. And I can see I got this y coordinate 7.96. Well, I'm thinking that I'm going to be approaching a y coordinate of 8 right now. But to confirm, get closer. Okay, 7.996, getting closer to 8. Let's get closer. We are thinking about getting infinitely close, having a distance that's an infinitesimal. We used that word infinitesimal for the first time last class. So infinitely close to a location. Eventually your calculator gives up and it will round on you. I don't want you to think that that means you have the 0.28. That's not correct. When you plug in 2, you get nothing, okay? But if you plug in something close to 2, like eventually my calculator, when I plugged in 1.999999999, it rounded up to 2. It doesn't like too many decimals. It can't show everything. And it rounded what is essentially 7.9999999. It just rounded that up to 8. So sometimes don't go too far. So you can see, like, as I get close to 2, I'm getting close to 8. So from the left, I'm approaching the y coordinate of 8. Let's do the same thing from the right. If I plugged in something just a little bit bigger than 2, like 2.001, well, I can see, yeah, I'm getting close to 8 as well. Let's get even closer to make sure. Yep. If I went too close, my calculator would round. This is deceptive. This is not correct. This is just your calculator rounding. What is 2.000000001 and what is 8.0000001. So Maybe stop here just so you know that like I'm getting very close to 8. I'm approaching the y coordinate of 8. Since the left-hand limit equals the right-hand limit, my limit is that value 8. Okay? Let's look at sine x over x. Make sure your calculator is in radian mode. That's the first thing. You'll always be in radian mode in this class. We are only using radians. Go to mode, make sure you're selected to radians. Okay? Now we're going to start by graphing it, see what the graph looks like. All right, cool. Now I'm going to plug in 0. Well, I know if I plugged in 0, sorry, press trace first. Plug in 0, I get the sine of 0 over 0. I'm not allowed to divide by 0, so that's bad. So this is showing you that when you plug in 0, it's undefined. Okay, sine of 0 is 0. 0 over 0 is undefined. But you could look at the graph and be like, man, that's a hole. That's got to be a hole. It looks like I have a location of that hole. I can be approaching that location, so I'll have a limit. Let me show you. Like the limit as x approaches 0. We should look to the left of 0. We should look at the right of 0. And then that will confirm our answer for the limit in general. So the left of 0 is like a negative small decimal. I can see it's essentially at 1. Again, this is your calculator rounding. Boom. If I didn't go so close, it wouldn't round. As I get very, very close to 0 from the left, my y coordinate's approaching the y value of 1. If I go a little bit to the right, so that'd be a very small positive number, you can see I'm also close to this y coordinate of 1. I can plug this in because I'm not going to be dividing by 0. Okay, you can't divide by 0, but you can divide by something close to 0 because it's a number. The closer I get to 0, the more my calculator is going to round. This is 1 e to negative 6. That's like 10 times, that's 1 times 10 to the negative 6. 1e6, this is important to know because your calculator sometimes will deceive you. They'll give you this as an answer and somebody's like, what's that, 1.6 or something like that? No, that's 1 times 10 to the negative 6, which means take 1, move the decimal place over 6 times. So 1, 2, 3, 4, 5, 6. This is what I plugged into the calculator. The y coordinate is going to be very, very close to 1. My calculator is rounding because I'm so close to 1. They're like, well, you're essentially at 1. The left-hand limit equals the right-hand limit. Boom, that limit equals 1. Okay, now we get into piecewise functions. Piecewise functions make things tricky because it is with piecewise functions that we could potentially see jumps. Jump, a jump, a jump. Okay? We're using a specific equation for specific x values. For all x values less than or equal to 1, I'm going to use x. For all x values bigger than 1, I'm going to use 1 minus x. If I ask you what f of 1 is, well, you would say, well, I'm supposed to be using x for x's that are equal to 1. So if I ask you what is f of 1, I don't plug it into both of them. I plug it into the one where it's like, hey, for these x's, use this piece. So for the x of 1, use the piece x. I plug in 1 into that, and I just get 1 because like it's just x. So whatever your x is, that's your y. All right? Now, if I were to look at 1 from the left, I'm not going to graph this. This is actually too easy to graph, and it might be confusing because it's tough to graph piecewise functions. We're going to say, okay, numbers to the left of 1, like 0.99999. Okay, what would you use? You would use this piece. I'm using this piece when x's are less than 1. This is less than 1. That falls in here. So that means I'm thinking about plugging in 0.9999 in for x. And you might be like, oh, okay, my y value is going to be that value, 0.9999. But no, that's not the concept of a limit. Because we could get closer. We could get closer. We could get closer. If I keep plugging in these values, what value am I going to get really close to? 1. essentially the y coordinate here if I do plug in 1. Now let's think about 1 from the right. If I were to plug in 1 from the right, I would use something like 1.0001, something like that, or even closer. Well, we look up here to our piecewise function, and we are told that when x's are bigger than 1, you need to use 1 minus x. So I need to use this piece here. And I need to think about plugging in 1.0001 in here. Now, 1 minus 1.00001 is going to be something very, very close to 0. It's going to be a little bit negative because I'm subtracting more than what I started with, okay? But you're not going to put the answer of negative 0.0001, okay? Because, think about it, we want to get closer and closer and closer and closer. We want to get infinitely close to 1, just a little bit more than that. That's essentially like plugging in 1 into this piece. And if I plug in 1 into this piece, 1 minus 1 gives me the y coordinate of 0. So I'm plugging in something infinitely close to 1. I'm going to get something infinitely close to 0. We are approaching 0. Now, because the left-hand limit and the right-hand limit do not agree with each other, that's all I look at, I know this does not exist. That's it. Don't look at anything else. Just look at the left-hand limit and the right-hand limit to answer the limit in general. Now, the next sets of questions are not designed to confuse you, but it confuses a lot of students. A lot of students, after going through this set, think, oh, okay, I got this. Limit as x approaches 2. I need to plug in 2 here and 2 here. Or I just plug in 2 to this one because this is the one that I use for the left-hand limits. No, not the case. Let's think about it. If I wanted to focus on 2 from the left, I'd be plugging in 1.9999 for x. Do you use this piece if you plug in 1.99999? No, I'm only using this piece for x's that are less than or equal to 1. You use this piece when x is bigger than 1. That means I don't plug 1.999 into the top one at all. I don't have to worry about it because it's not going to be the function that I'm using for these values. I just need to focus on this bottom function. And I could just plug in 1.999 if I want to, but it's essentially like plugging in 2 into this one. And 1 minus 2 gives me negative 1. Don't have to look at the top at all. Don't worry about x. X is only for values that are less than or equal to 1. Let's look at 0 from the right. Okay, 0 from the right. You might be thinking, oh, right-hand limit. I got to use the bottom function. No, I'm only using this bottom function when x's are bigger than 1. I'll show you how to get the same answers graphically if you want to do this by hand. You're thinking about plugging in 0.00001. That's the value. That is approaching 0, but it's just a little bit bigger. That's going to use this piece when x's are less than or equal to 1. That's like plugging in this value in here. Well, as you get closer and closer to 0, you're plugging in values that are closer and closer to 0 in for x. It's like plugging in 0 for x. At 0, your y coordinate is 0 because it's just plug in the x, you get that y. Don't care about the bottom piece at all. It's not going to worry us. As x approaches 3, okay, this is not a one-sided limit. This is in general. You should think about, though you'll find that it's not something you'll have to worry about, the left-hand limit and the right-hand limit. Three from the left is like 2.9999. 3 from the right is like 3.0001, infinitely close to 3. Well, you don't worry about the top piece. The top piece is only used for x's that are less than 1. I'm talking about 3. That's bigger than 1. I'm talking about 2.999, 3.001. That's bigger than 1. So I need to plug in 2.999 here, 3.001 in here. But both times I plug it in, it's essentially the same as just 1 minus 3. Whether it's from the left or from the right, 1 minus 3 is negative 2. 1 minus 3 is negative 2. Okay? It's either like negative 1.999 if it was from the right, or negative 2.001 if it was from the left. But it's approaching negative 2. The left-hand limit and the right-hand limit agree with each other. The limit in general is negative 2. Okay? Now, if you wanted to do this graphically to visualize the answers that we just provided, here's what you would do. You would try to sketch the graph yourself. It is not hard to do. We're focusing on this x-coordinate 1. For x is less than 1, so that's like 0. That's like negative 1, negative 2. I'm going to use y equals x. Well, the y-coordinates are equal to the x-coordinate, so if I have an x-coordinate of negative 2, my y-coordinate is negative 2. Negative 1, 0, 0, 1, 1. I'm going to put a closed circle at 1 because I am plugging in 1 in for x. This is my first piece of my piecewise function. This goes on forever. Now the second piece starts at 1. So like you can't plug in 1, but you can plug in 1.00001. Okay, if I plug in 1.0001, I'm getting something close to 0. Okay, so maybe it's like right there. Well, if I plug in 1.000000001, I'm getting even close to 0. What we do to indicate that we are going to be approaching this y-coordinate 0, because it's like 1 minus that number very, very close to 1 is going to equal 0, I'm going to use an open circle to be like, hey, you're going to go up to, but not include that 0.10. You're going to be approaching that point. And then from there, if I plugged in 2, 1 minus 2, negative 1. I'm down here. If I plugged in 3, 1 minus 3, negative 2, down here. If you could create this graph, then you can easily see our answers. 1 from the left. If I'm just to the left of 1, I'm up here. I'm approaching this y-coordinate 1. 1 from the right. If I'm just to the right of 1, I'm using the other piece, the red piece. As I get closer and closer to 1 from the right, I'm approaching that open circle's location at 0. Limit in general at 1 does not exist. We have a jump. 2 from the left, just to the left of 2, I'm approaching this location of negative 1, that y-coordinate. 0 from the right, as I'm really, really close to 0, but just a little bit bigger, well, I'm approaching that y point, that y-coordinate of 0. 3, if I'm at 3, I don't care about this piece. I just care about this piece, the red piece. I'm approaching that y-coordinate of negative 2. Okay? All right. We want the one-sided limits and general limits for this function at negative 2, negative 1, 0, 2, and 3. Well, we can see we have 3 pieces. X squared, 3x plus 4, 11 minus x. X squared until negative 1, 3x plus 4 from negative 1 to 2, 11 minus x after 2. If I asked you what's going on at negative 2 of this function g of x, okay, you look at your domains and you realize, okay, I'm just using negative 2 with this piece. So really, this is the same as the limit as x approaches negative 2 of just x squared. It's just like if I plugged in, negative 2.0001, negative 1.99999, you'll get the same thing, which is just negative 2 squared, and I get 4. That's an easy one because I'm just focusing on x squared. Negative 1 is going to be tricky. I got 2 pieces. I know 0 is going to be easy. Let's take care of the easy ones. X equals 0 is going to be easy. Why? Because if I'm using x's that are close to 0, I'm just focusing on this piece. So that piece, 3x plus 4, if I looked at the limit as x approaches 0 from the left, it would equal the limit as x approaches 0 from the right, which is really just equal to the limit as x approaches 0 of 3x plus 4, which is really just equal to like plug in 0 into 3x plus 4. Maybe I should have shown that for the last one. And I get 4. I know that. If I plugged in negative 0.001, I'd plug it into 3x plus 4. If I plugged in 0.0001, I'd plug it into 3x plus 4. Let's do that here. Let's, instead of doing this, be like, this left-hand limit's got to be equal to this right-hand limit, which has got to be equal to the generalized limit of x squared, which is equal to me plugging in negative 2 into x squared, which got me positive 4. Okay? What's another easy one? 3 is easy. Why is 3 easy? Because I don't have to worry about jumps between pieces. I know that when x is 3, I'm just using this piece. So I'm going to say x equals 3. That's easy. The limit as x approaches 3 from the left will equal the limit as x approaches 3 from the right, which equals really the limit as x approaches 3 of 11 minus x. To find that limit, since it's nothing crazy, no jumps, no asymptotes, I just need to plug in 3 into 11 minus x. Maybe I'll show that step. 8. Here, I would plug in 0 into 3x plus 4. And here, I'd plug in negative 2 into x squared. Okay? Used a lot of space for those 3, but it's necessary. Now let's go to the ones where we need to investigate further, where we have potential jumps. Starting with negative 1. Okay? We got to look at negative 1 from the left. We got to look at negative 1 from the right. And then looking at those two numbers, we'll be able to answer negative 1 in general. Okay, negative 1 from the left. Negative 1 from the left, that's like negative 1.0001. That's a little bit less than negative 1. I'm going to use the top piece when I'm less than negative 1, which means I'm going to be plugging in negative 1.0001 into x squared. It's going to be getting closer and closer to what happens if I just plug in negative 1 into x squared. I am going to just plug in negative 1 into x squared, and I get 1. And that's what I'm going to approach if I'm just to the left of negative 1. If I'm just to the right of negative 1, like at negative 0.9999, I'm using this piece when x's are bigger than negative 1. This piece uses 3x plus 4. Okay, so I'm plugging in what I'm thinking about, negative 0.9999 into 3x plus 4. But I'm getting closer and closer to plugging in negative 1. So we can just plug in negative 1 to see what y value we're going to approach. We don't have to use our calculator for this. I'm just going to plug in negative 1 into 3x plus 4. Get that y coordinate, 1, and that is our right-hand limit. Now, even though we have two different pieces, what ends up happening, and you could see this if you wanted to, is that the x squared stops at negative 1, 1 with an open circle. But the 3x plus 4 starts at negative 1, 1. I should be using blue. which means this piece meets up with this piece. They don't jump, they connect, they match up. 3x plus 4, I can plug in 0, I get 4. So it's like this line up here, getting us to 4. Okay, and I'll just stop there. We already know that I'm approaching 4. Since the left-hand limit equals the right-hand limit, even though we have two different pieces, since we meet up, we're approaching this y-coordinate of 1 at that location. So the limit exists. We would say that this function is continuous at -1. Let's look at the other potential jump, which is at 2. Because at 2, I go from this piece and I switch over to that piece. So we'd have to evaluate, and I'm kind of just walking you through step by step what you have to do. You can get these answers a lot quicker if you understand what's going on. The limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and then we'll get 2 in general. Okay. 2 from the left. I'm using this piece again because we're talking about using x's between -1 and 2. So if I were to plug in 1.999, I would plug it into this piece. Plugging in 1.999, plugging in 1.9999999 is essentially going to give us the y-coordinate that we will approach if we plugged in 2 into this piece. You might be thinking, but we're not supposed to plug in 2 because it's x's that are less than 2. Yes, I know. But what's going to happen if we plug in 2, 3 times 2 plus 4, which is 10, is that we are going to figure out the location of where we end this piece, where we end up having an open circle for this piece. Because I'm plugging in 1.9, 1.999, 1.999, and we're going to get closer and closer to the y-coordinate 10, but I'm not allowed to plug in 2, okay, if I'm looking at the function. I essentially am, because we know, like, if you keep plugging in values closer and closer to 2, just to the left of it, it's like plugging in 2. That's the y-coordinate you're going to approach. So this is 10. Now, if I looked at 2 from the right, we'd be using this piece. Okay, if I plugged in 2.001, that's a value that's bigger than 2. Okay? Now, if I plug in 2.001 into 11 minus x, I'm going to get something close to 9. As I keep plugging in 2.0000001, closer and closer and closer to 2, I'm going to approach the y-coordinate where I actually plug in 2 to, like 2 into that. 11 minus 2 is 9. 11 minus 2.0001 is close to 9. So we can see that we would be approaching that y-coordinate of 9. So it's very interesting. This last piece, this blue highlighted, starts here with a closed circle. It starts at a y-coordinate of 9. And then we'll have 11 minus x, that graph. So you can see we connect, but then we jump. It's because we jump, we see the left-hand limit, the right-hand limit don't equal each other. The limit in general at 2 does not exist. Okay? Make sure you go through this process yourself and understand why we are doing what we're doing. Okay? Obviously, like, you can just plug in values, but you just got to know what values you're plugging into and why we're plugging into. Now, these next 7 functions, I'm saying you can't use your calculator, but you need to find the limits. Okay? And it's like, well, what do you do? Like, I've been able to plug in like values into my calculator like I just did for like sine x over x. Like, how do I plug in 1.999 here, 2.001? Well, the key to all these functions is that they don't have any like weird locations. They don't have any holes. They don't have any jumps. They don't have any asymptotes. They are just nice, smooth, continuous functions where I can plug anything in and I'm never going to have a 0 in a denominator. This is what's called a continuous function. And typically, limits equal function values. Like if you are continuous, no holes, no jumps, no asymptotes, your limits and your function values agree. That's just simple. I could make it more correct. So like, don't worry about plugging in 1.999. Don't worry about plugging in 2.001 because it's just going to be plugging in essentially values close to 2 into x squared minus 1. I can plug in 2 into x squared minus 1, and I get 3. Well, plug in 1.999, you're going to get something close to 3. Plug in 2.001, you're going to get close to 3. That's the function value, which equals the limit. This is like this situation we had up here at 3. Okay, x squared minus 1 is just like a function that always connects. And at 3, we have a point, and we're approaching that point. For this situation, it was like zeros all the way down. Okay, that's the same situation for all 7 of those. You don't have to stress because the function value and the limit will agree with each other. Find the function value. You would approach that value from the left and the right if you plugged in negative 0.001 or 0.001. It's just like the cosine of 0, which is just 1. Plug in something a little bit to the left of 3 pi over 2, a little bit to the right of 3 pi over 2. It's just like plugging in 3 pi over 2 into sine. Sine of 3 pi over 2 is negative 1. Why? You're going down. Y distance negative 1. And the others are the same way. Just plug in pi over 6. Just plug in pi. Secant pi over 6. Secant's the reciprocal of cosine. Cosine pi over 6. 30-degree angle is the pi over 6. Cosine is the adjacent side. That's the longer side. So I need the reciprocal, which is 2 over root 3, which we know is 2 root 3 over 3 if you rationalize. Plug in pi into e to the x. What? Well, guess what, guys? Like, if you don't have a calculator and you can't simplify, you're just not going to. That's your answer. E to the pi, whatever that is. I'm trying to trick you here, just so we know this and this are different. This is a good one. If I plugged in 4, order of operations would say, take that 4, square it first, then make it negative. The answer to this is negative 16. But you might be thinking, well, isn't a negative number squared positive? Yes, but the way we do this is thinking about this negative as being like negative 1 times. If I asked you to do order of operations, what do you do first? Exponents or multiplication? You always say we do exponents first. So that's why you think about 4 being squared and then multiplying that by negative 1. This is just a common mistake made from all students of all levels, is like messing up this and telling me that this is positive 16. We'll see this often. However, for here, if I plugged in negative 4 in for x, I'm taking x, plugging in negative 4, squaring that negative number. If you square that negative number, you get a positive. This is like a quick heads up. If you're using a calculator, which we don't use often, your calculator is very deceiving. If you plug in negative 4 squared, you're thinking, oh, it's positive 16. Negative 4 times negative 4, positive 16. But then your calculator tells you, no, it's negative 16. Why? Because it's using order of operations. It's saying, hey, negative 1 times 4 squared, I'm going to square that 4 first, and then I'm going to multiply by negative 1. That's how it gets negative 16 when you plug that in. But you know, negative 4 quantity, the number negative 4 times itself, that gives you positive 16. That's what we want for this one, not what we get for that one. Okay? I hope you understand limits. The key concept that we're going to bring forward is the idea of getting infinitely close to something. Okay? Infinitely small distances. Infinitely small distances are used to help explain calculus. Okay? Small things are used often in calculus. Thanks for watching.